Hello. This is Math 2134 coming to you from the College of DuPage, and the title of this lecture is The Chain Rule. So we're introducing another rule of differentiation. It's called the chain rule because this picture looks something like a chain. When you use this in conjunction with the rules of differentiation that we've talked about already, it greatly enlarges the class of functions that we're able to differentiate. And the basic issue is that we're doing composition of functions. So we're doing f, and then we're doing g, and the composite function is going to be h, that is going to be g composed with f. Now it makes sense that the rate of change of h depends somehow on the rate of change of f and the rate of change of g, and that's what we're going to be looking at. And we're going to be taking the derivative of y equal g of f of x. So here's a statement of the chain rule. This first statement that's shown here with number 1 is you're taking the derivative of this. So first you take the derivative of g with respect to f of x, and then you take the derivative of f of x. My students tend to think it's easier to think about this way, that y is equal to g of u, and u equals f of x. So dy dx is equal to dy du times du dx. It almost looks like these du's are canceling, and that's an easy way to remember the chain rule. If we apply this to a power situation where we have h of x is equal to f of x whole to the n, where n is a real number, then h prime of x is equal to the derivative, and you take the derivative of what's on the outside first, so it's going to be n times the business in the middle to the n minus 1, but then you have to take in turn the derivative of f of x. Some mathematicians have said using the chain rule is like peeling an onion. You have to start with each layer at a time, and if it's too big you start to cry. That's a little bit of a joke because my students don't cry. We just do the problem. But this is sometimes a useful analogy because we're working from the outside of the onion inward, layer by layer. Nothing like working some examples. We'll do several. So here we have f of x is equal to 3x plus 1 whole to the square. So when we use the chain rule and take the derivative of capital F of x, it's going to be, we start on the outside, which is the squared function. It's going to be 2 times this business, now raised to the 1. But then we have to take the derivative of what's inside. So that's the derivative with respect to 3x plus 1, which is 3, and this is what I get. Now, if we had done this previously without the chain rule, we could have just squared this and gotten this and taken the derivative, but you get the same answer. So that's our first example of the chain rule. Here's another one. So we have g of x is equal to this business, the square root of that. Well, we're going to write that as g of x is equal to x squared plus 1 whole to the 1/2. Now the function on the outside is the square root function, and on the inside I have this other function. So using the power rule with the exponent equaling 1/2, I'm going to have that this derivative is going to be 1/2 this business to the minus 1/2. But then I have to take the derivative of what's inside, the next layer of the onion. So that's the derivative of x squared plus 1, and that's going to be 2x. So we get this, and often algebra is your friend, and this can be simplified this way. This time we're going to be looking at the product rule. So first we have the first function is x squared, but the second function is going to be 2x plus 3 whole to the 5th. So you see this second function is going to be using the chain rule. So you see you can use the product rule with the chain rule. So here's the function. We're going to take the derivative, so it's going to be the first function times the derivative of the second, plus the second function times the derivative of the first. So that's just x squared. When I take the derivative of this, it's going to be, taking the derivative of 2x plus 3 to the fifth, that's going to be 5 times all of this business to the fourth, times the derivative of what's inside. Plus, then it's going to be 2x plus 3 whole to the fifth, times the derivative of x squared, which is 2x. So then I do the algebra, and it can be simplified this way. Here's a more complicated product rule. So here the first function is going to be 2x squared plus 3 whole to the fourth. The second function is going to be 3x minus 5 whole to the fifth. It's going to work the same way, but both of these functions have the chain rule. So applying the product rule, we're having the first times the derivative of the second plus the second times the derivative of the first. So when I take the derivative of this one, I'm going to get 5 times this business to the fourth times the derivative of what's inside. That's going to be a 3. And over here, I'm going to take this expression times the derivative of this. So this is 2x squared plus 3 whole to the fourth. So it's going to be 4 times this business, whole cubed, times the derivative of what's inside, which is going to be 4x. So we do some algebra, realize what I have as common factors, and I can simplify it to this expression. Here's an example 5. We're looking at y equals f of x is 1 over denominator of 4x squared minus 7 whole squared. Now, what we're really going to do is we're going to think about this as being raised to the minus 2. So you see I've got 4x squared minus 7 whole to the minus 2. So the derivative of this is going to be minus 2. This business, now subtract 1 to the minus 3 times the derivative of what's inside, which is 4x squared minus 7. And when you take that derivative, you get 8x. You simplify this, and you can get this expression. Here's example 6. We want to find the slope of the tangent line to this function. This is y is equal to 2x plus 1 divided by 3x plus 2 whole to the third, and at a specific point. So you see the derivative is going to be the slope of the tangent line at this curve, and so I'm going to take the derivative and then substitute x is equal to 0 into my problem. Okay, so you're going to be having the outer function is something being cubed. The inner function, though, is the quotient. So this time we're using the quotient rule. Okay, so the derivative of this is going to be 3, that business, squared, times the derivative of that business. So it's 3, that squared. But then this is a quotient rule. So it's going to be denominator times derivative of the numerator minus numerator times derivative of the denominator, all by the denominator whole squared. There's a lot of algebra that you can do with this. Actually, not so much, but you work to combine like terms, and we can simplify it to this expression. So if we plug 0 in then for x, we get that this is 3 over 16. I am typically going to ask you to get numbers, and how much simplification you do depends on you. But algebra is your friend. It makes the problems less complicated. Life is a word problem, so we're going to do word problems here. The Growth and Health Club is this, and you see we do have a chain rule because we've got this business raised to the 2/3. So we're to find the derivative, and we're also supposed to find the derivative evaluated at several values. So let's talk about finding the derivative. First of all, the constant just sits there, so I'm really taking the derivative of 64 plus 4x whole to the 2/3. So this is going to be, pull the constant out of the derivative, and this is going to be 2/3 this business. I subtract 1 from 2/3 and get minus 1/3 times the derivative of what's inside the next layer of the onion. That's going to be 4. And so this is the expression I have, which can be simplified algebraically into this expression. So if I plug these numbers in that they're asking us to plug into this formula, and I usually will ask you to plug in numbers, we get that it's about 67 people per week is the growth when it first opened. At the end of the 40th week, it's increasing by about 44 people per week. And then they ask you, what was the membership when they first opened? Now that goes all the way back to this equation. You have to keep track of where you plug it in, but you get that there were 3,688 people. Let's look at another example. This is from the medical or life sciences. So you have a disease, you start building up plaque around your blood vessels, and so what we have is that the area for the blood to flow is given by pi a minus h squared. The outer radius is a, the inner radius is, let's see, the outer radius is, we're taking a to be 1, so what we get is, this is the area of the opening, pi times the radius squared. So we have that, and we have the area, but we want to know how is that area changing with respect to time. So you see the area is equal to pi times, but it is 1 minus h squared, where h is this function that they knew experimentally. So you see, this is one of those things where some students would start to cry because you're really doing a chain rule multiple times. First you find out what h is, and then you plug it into this equation. So you see you've got the chain rule several times. T goes to h, and h goes to a. So dA dt is equal to dA dH times dH dt. So dA dH, here's a, is going to be, pi just sits there, but then it's going to be 2 h, 1 minus h, whole to the 1, times the derivative of what's inside, which is minus 1. But now we have to take dH dt, and here is h, and you see that's kind of complicated. You got multiple terms, and so when you take the derivative of this, the derivative of 1 is just going to be 0, and the constant just sits there, but the derivative of this expression is going to be 1/2 this business to the minus 1/2, and then I have to take the derivative of what's inside, which is minus 2t, and then I have another term over here, which is that by the chain rule. So we can simplify that, and then if we want to know at a given time when t is equal to 50, we would plug in 50 and we would get the answer. Again, I'm going to be asking you to plug in numbers often. Algebra is your friend. It makes it easier to plug in numbers, but how much algebra you do is up to you. In closing, now more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now more than ever, take care of yourself and of each other. God bless you all.